our topic for this video is the thin-walled pressure vessel, the tangential and the longitudinal stress. Okay, for this video, then we will show uh, where does the formula derive from, the formula for the tangential and then the longitudinal. We will solve also problem for the application of the derived formula. Okay, so what is thin-walled pressure vessel? It is a tank or a pipe carrying a fluid or gas under a pressure is subjected to a tensile forces which resist bursting, develop across longitudinal section, or the the stress developed from the longitudinal section is the tangential stress, and the transverse section which produce a longitudinal stress. Okay, so let's draw a tank. Okay, so if this is the tank or a pipe. Okay, so let's imagine where is the bursting point or the failure of this tank if the pressure inside is too high. So okay, one is uh, the tangential stress. Tangential stress develops along the longitudinal section is one. Okay, and then the other one is the transverse section which produce a longitudinal stress. We will call it longitudinal stress. Okay, so uh, let's try to cut this tank along the longitudinal. So this one. Okay, so if we cut this one and then pressure, let's show the the forces acting inside the tank. So the F is the pressure from the gas or fluid, and then from the pressure, the tank will resist also to hold the pressure in equilibrium. So the tank will resist the T and T for the both side of the the tank. So if we can see, we call it the tangential stress since the force acting from the vessel is tangent from the pipe. Okay, so they call it tangential stress. Okay, so let's derive the formula. So from our fluid mechanics or hydraulics, the pressure is equal to P over A. Okay, and then P, let's substitute the P into F. Okay, so this one, so P is equal to F. Okay, and then the area is the length and the diameter. This one, the diameter and the length. Okay, so okay, from the formula of the uh, pressure is equal to P over A, we can say that pressure is equal to F, this one, divided by the area, which is the diameter multiplied by length. Okay, so F, we can say that F now is the uh, pressure multiplied by dl, this one. F is equal to pressure multiplied by the diameter times length. Okay, so this is the value for the F, and now let's compute the value of T. Okay, so from our previous topics that stress is equal to P over A. Okay? And let's assume again that P is equal to T. Okay? And then the area is equal to L is 1, the length multiplied by the thickness. This one, the thickness of the vessel. Okay, that is the area of the stress developed from this side. Okay, so from this uh, from this formula, we can say that T is equal to stress, tangential stress multiplied by area, which is length times thickness. Okay, so that is the value for T. And then let's do the summation forces horizontal. F is equal to 2T, this one. Okay, this is the F and T. Okay, so from this equation, F is equal to rho dl, pressure, diameter, and length times 2 is the 2. And then the T is the tangential stress multiplied by length and thickness. So we can say that the tangential stress is the pressure multiplied by D over 2T, this one. Okay, so as we can see, the length, the L will cancel out. Okay, so the stress formula for tangential stress is rho D over 2T. Okay, so let's proceed to the longitudinal stress. Okay, so here is the figure. So okay, if we will cut it, we can see the uh, internal forces due to pressure, the F, and the T is the internal pressure resisting by the vessel or a tank. Okay, so from the formula again, uh, pressure is equal to P over A, and P is equal to F, and then the area is the area of a circle is AD squared over 4. So this one, the area of this one. Okay, and then let's substitute rho is equal to what is P. We will replace it by F, and then the area is pi d squared over 4. Okay, and then we can say that F is equal to rho pi d squared over 4, this one. F is equal to to rho pi d squared over 4. Okay, so this is the value for F, and then let's solve the value for T. Okay, from the stress, longitudinal stress is equal to P over A. And then let's substitute again the P by T. Okay, and then the area is equal to pi dt, the area of this one. Okay, so pi d, okay, pi d is the circumference of the inner dimension of the uh, tank, then multiply it by the thickness. Okay, and then so T is equal to this, from this formula, T substitute by P substitute by T, and A substitute by pi dt. So T is equal to longitudinal stress multiplied by pi dt. So that will be the value for the T. Okay, and then let's do the summation forces horizontal. Okay, F is equal to T. And then, what is the value of F? Is the rho pi d squared over 4 is equal to, what's the value of T? tangential longitudinal stress multiplied by pi dt. Okay, so from this equation, we can say that the longitudinal stress uh, is equal to pressure multiplied by d over 40. Okay, so this is now our equation, the derived equation from the uh, to get the longitudinal stress of the vessel. Okay, so from this formula, we can say that tangential stress is equal to twice the value of the longitudinal stress. Since they have the same rho d, and then the difference only is the divisor, which is from the tangential is 2, and then from the longitudinal is 4. So from these two equation, we can say that the tangential stress is twice the value of the longitudinal stress. And then so we can say also that the uh, bursting uh, point of the tank is always on the tangential part, this one, based on this formula. Okay, so let's try to solve problem for the application of this derived formula. Okay, okay, so here is the problem. A cylindrical steel pressure vessel 400 mm in diameter with a wall thickness of 20 mm is subjected to an internal pressure of 4.5 uh, megapascal. Okay, so calculate the tangential and longitudinal stress in the steel. Okay, to what value may be the internal pressure be increased if the stress in the steel is limited to 120 megapascal. Okay, letter C. If the internal pressure were increased until the vessel burst, sketch the type of fracture that would occur. Okay, so let's solve the letter A, the tangential and the longitudinal stress. Okay, so let's solve first the tangential stress, and then let's draw the illustration. Okay, so this is the force uh, due to pressure, and then this is the force due to resisting of the tank. Okay, so from our previous derived formula, okay, so the tangential stress is equal to pressure times d over 2t. Okay, so substitution, the pressure is 4.5. Okay, so 4.5 megapascal. So 4.5 meganewton over meter square is the same as 4.5 newton per mm squared. Okay, so we will multiply it by the diameter. So what's the diameter? The 400 millimeter divided by 2, and then the thickness of 20 mm. So tangential stress is 45 megapascal. Okay, let's solve the longitudinal stress. Okay, so let's draw the illustration. Okay, and then the internal force due to pressure, and then the internal force due to the resist of the tank. Okay, so from our formula, uh, longitudinal stress is equal to pressure times d over 40. Okay, so the pressure is the same, 4.5 megapascal times 400 mm over 4 times 20 mm. So the longitudinal stress is 22.5 megapascal. So from our previously discussed that the critical is at the tangential stress. It is always twice the value of the longitudinal stress. Okay, so let's proceed to letter B. To what the value may the internal pressure be increased if the stress in the steel is limited to 120 megapascal. So the problem is he's asking for the pressure, required pressure, as not to burst the steel tank with the stress steel limit of 120 megapascal. So what can we use, the tangential or the longitudinal? Okay, so as earlier mentioned, that the critical is the tangential stress. So we will use this one. Okay, so from the tangential stress is equal to rho d over 2t, and the tangential stress is limited only to 120. Okay, and then the rho is the unknown multiplied by d, 400, and then divide by 2t. So the rho, the maximum pressure that the tank can hold if the uh, stress limit is equivalent only to 120, is the pressure is only 12 megapascal. Okay, so for checking, let's try to solve uh, for this formula, the formula for the longitudinal stress, only for checking. Okay, let's check. Okay, so longitudinal stress equal to rho d over 40 is 1. Okay, so let's substitute 120. Rho is the unknown multiplied by 400, divide 4 times 200 mm. So the pressure for this uh, for this formula or this consideration is 24 megapascal. Okay, so meaning if we apply 24 megapascal, uh, the longitudinal stress will not burst, but the tangential stress uh, will burst. Okay, since the pressure capacity only is the 12. Or how about, let's say we apply 12 megapascal from tangential stress. It is safe, okay, since the stress limit is attained. Okay, and then for the longitudinal stress, if we apply the pressure of 12 megapascal, okay, the longitudinal stress will not overstress. It is lower than the value of 120 mm. Okay, so the answer for letter B is the 12 megapascal. This is only for checking. Okay, so the answer for letter A is the tangential stress is 45 megapascal and the longitudinal stress is 22.5 megapascal. Okay, and then the letter B, to what the value may the internal pressure be increased if the stress in the steel is limited to 120 megapascal. Okay, so the answer is 12 megapascal. And then let's proceed to letter B. If the internal pressure were increased until the vessel burst, sketch the type of fracture. So as discussed, okay, that the most critical is the tangential stress. Okay, it can hold only half for the consideration of the longitudinal stress. So if we will sketch the bursting uh, fracture, it will occur the, the uh, in the longitudinal section. This is what we call the longitudinal section. Okay, so thank you for watching.